Hi, oh, how you doing?
Hi, I'm
Hi,
alright.
Jessica. Who's Ethan? How you doing? Is that you talking?
Yeah,
Okay, you guys either did really, really well or not so good on the test. I tried to make it easy for you. First three questions are just simple plug-in things. You should have expected the chart, the indicator chart, and the titration curves. You should have expected that in there because I spent a whole bunch of time on those things. All right, that's my say. Go for it. Any complaints, guys?
I had a question about a question on the test.
Okay, Manuel, what you got?
I'm pretty sure it was a multiple, it wasn't a calculation one, but you had given us the base to be 1, and I think the acid to be 0.1. And then
The conjugate base was 1 and the weak acid was 0.1, right?
yep. And then
So that's the
yeah,
log of 10. The Henderson-Hasselbalch is pH is equal to pK plus the log of conjugate base over conjugate acid, right?
Yep.
The ratio conjugate base to acid is 10 to 1.
Okay, so it was 10.
Log,
It was 10
yeah,
times.
It was 1 molar to 0.1, right?
Mm-hmm.
So if you divide the 1 molar by 0.1, that gets you 10, right? So you have the log of 10. Log of 10 is equal to 1.
Yeah, because okay. So pH does not equal pKa. Like that's
No.
only if it's equal if
The only way
log of 0 or log of 1.
The only way pH is equal to pKa is if the log of the concentrations are the same. If the concentrations are the same, then that's going to be the log of 1. Log of 1 is equal to 0. pH is equal to pKa.
Okay. That's what I was thinking. Because when I saw 1 on my calculator, I was like, oh, pH must equal pKa, but yeah, never mind. Okay, that was my question.
You did okay, Manuel. You did okay on that test.
Could have done better. Could have done better. But thank you, though.
This is not an easy subject, especially what we just went through. It is not an easy subject. It is what it is, guys. And you're taking it at a very rapid pace. Any other questions?
Is there going to be extra credit again?
I'm deciding on that, Emily, and you don't need it. You did very well on this test. Emily, did you see your score?
Yeah, but it could have been better.
Oh, come on, Emily. No, you did fine. You did fine on it. There will be a little extra credit.
can we go over like question 8 on it? Or I'm sure. Wait, is it this? Is question 8 the same for every one? Or
All right, yeah. Is that the one, the KSP problem with the
yeah.
copper and the chromate?
Mm-hmm.
All right. What you had to do is, let me go to share screen and this thing. Ethan, do you have it pulled up?
I do.
Okay, give me the concentrations. The copper
Okay.
concentration.
Let's see. When
Give me the
140
140.
milliliters of 5.0 times 10 to the 9 more
Sorry,
NH14.
you can't, you got to be slow about that. 5.90 e to the minus 10.
No, like 5.00, and then 10 to the negative 9
Okay.
more.
Now how about my
NH
chromate?
Oh wait, that one was for the oh wait, sorry, that one was for the chromate.
And the copper was
60 milliliters of 6 E negative 9.
okay. You're mixing these two together, right?
And it says the KSP is 5.65 times
Okay.
E negative 28.
KSB is what?
5.65 E negative 28.
Okay. Now you have to understand that what you're doing is that is, I'm doing that. This is what my equation is, right?
Yes.
Ethan?
Mhm.
So my KSP is going to be equal to my Cu concentration quantity squared times my CR207 quantity, right?
Yes, I got like that part.
All right, you're agreeing with, or better yet, I'm going to say Q because it's not at equilibrium, right?
Oh wait, that's the Q.
That's the Q. The Q is nothing more than the equilibrium expression when it's not at equilibrium. That's what Q is. Now, what I have to do at this point, Ethan, is I have to find the new concentration of Cu because I put the 60 milliliters in to 140. I have to find the new concentration of CR207 because I put the 140 in with the 60. So if I'm going to deal with the Cu plus, I've got 0.060 liters times 6 E minus 9th molar, and that equals
Is that equal like the KSP we're given, or?
nope, that's just the moles of copper.
Oh, okay. Yeah, just for that, let me just put
Okay, 0.06 times
6. 3.6 E negative 10.
Okay, thank you. My calculator, I got a crappy TI calculator, 30X. 3.6 E to the negative 10th.
Yeah, that's what I got. 0.06
Okay.
times 6 E negative 9. That's, yeah.
That's moles, right?
Yes.
I have to divide that by the new volume, which is 0.200 liters.
Okay.
Give me what that number is.
Okay, so divided by 0.2.
Should be somewhere like 1.8 times 10 to the minus ninth.
Wait, where does the 0.2 liters come from again?
Because the total volume is 140 and 60 milliliters. So that's 200 milliliters or 0.2 liters.
Oh, okay. All right, so that divided by 0.2 is 2e negative 9.
1.8. Okay.
Oh, I guess my calculator just didn't round to that far.
Rounded too far, actually. All right. So my chromium, on the other hand, my chromate, that's equal to 0.140 times 5e negative 9, which equals how many moles? Come on, I need you to do these calculations quicker. 0.140 times 5e negative 9.
Okay, 7e negative 10.
7.0 e negative 10. I'm dividing that by 0.200 liters. Do that math. I'll be right back.
Okay, my calculator rounded to 4e. Oh, but,
Okay, Ethan, you got that math for me.
my calculator rounded to 4e negative 9.
We'll go
but-
3.5 e negative 9.
Hmm.
All right. So now,
Okay.
now all I got to do is plug the 1.8 e to the ninth into copper squared and this number into chromates to the first. Do that number. I'm going to get a big number. I think it was times 10 to the minus 22nd,
Okay, so
26th.
1.8. 1.134e negative 26.
Yep. Okay, so that means that my Q is times 10 to the minus 26. My KSP was times 10 to the minus 28. What's bigger, Q or KSP?
Q.
So if Q is greater than KSP, it's going to go back towards the original salt. I do have precipitate present.
Okay.
All right.
I have a question.
Who's I?
Emily,
Hi, Emily. Okay.
I did this exact math on my exam and I got points taken off.
What did the comment say?
It said I switched the chromate and the CU, but we just did it and I'm looking at it and I did the exact same thing and got the exact answer.
Emily, I'm only reporting out what I've been told. Okay.
So what does that mean?
Ethan just reported the question out to me.
Okay.
If there's like any details like I didn't like communicate right, then you can like correct me.
Emily, I'll have to pull up your question. Is that okay with you?
Yeah.
Okay, 6. I'll look into it, Emily. I can't spend the time doing it right now.
Okay.
I will look into it and email you. Any other questions, ladies and gentlemen?
I have a question. It's
Is
Benita.
I- Yes, Benita.
It's about the precipitation one with the like the two. There's multiple choice. Hold on, I gotta find which question it was. Dude, it's 16. So what's the? So is it? How does it go again with the KSP value? Is it the smaller or the?
If Q is greater than KSP, then you got to get rid of products. Okay, Benita? If Q is greater than KSP, you got to get rid of products. So this means there has to be a precipitate.
Wait, no, not that one. The one that like which one precipitates out first?
The okay, the one with the lower KSP precipitates first because you're going to reach that level of ions first. So the one with the bigger negative exponent will precipitate first.
Oh, with the bigger. Okay, that makes sense. All right. Thank you.
Anything else, guys? Come on, anything else, ladies and gentlemen? If not, I'm going to begin entropy in a second. Countdown, 5, 4, 3, 2, 1. Good. Stop share. Share screen. Benita, how many kids are you holding around there?
I just have one.
It seems like more.
Feels like more.
Okay. Are we all seeing the slideshow, ladies and gentlemen? Entropy, this is one of the reasons why I am not a physical chemist. Thermodynamics. This is a very hard, it's the only subject I've ever encountered in which I have not been able to figure out what's going on 100% while I was taking the course. When you're dealing with this in physical chemistry, you're dealing with the calculus derivations of all these formulas. We're not going to get that far. We're just going to do the algebraic derivation. So what we're going to do, we're going to deal with spontaneity. We're going to deal with the entropy itself, and we're going to rate entropies. We're going to deal with the second and third laws of entropy, deal with Hess's law, deal with entropy and spontaneity. There's going to be a new term, Gibbs free energy. We're going to predict spontaneity from Gibbs free energy, calculate standard entropy, We're going to deal with standard entropy and standard Gibbs energy in equilibrium and Gibbs energy at non-standard conditions. I've given you the topics I believe are important here. Now, review. First law of thermodynamics. It said energy cannot be created, cannot be destroyed. Therefore, the energy of the entire universe is a constant. I'm not saying anything you haven't been told, right? You all had this in Chem 1, correct? It can, however, be converted from one form to the other or transferred from the systems to the surroundings or the surroundings to the system. Now you have to understand our definition of system. It's whatever you say it is. If you say it is this room that I'm sitting in, then everything outside of this room is the surroundings. I can transfer energy from this room to the surroundings or the surroundings to this room. That is allowed under the first law of thermodynamics. So guys, why does ice melt? Why does ice spontaneously melt at room temperature? Emily, got an idea?
No.
Ethan?
Is it because like the like the temperature of the surroundings of like the ice is like higher than the temperature of the ice, like the.
But why does temperature go from the surroundings into the ice to do that?
Well, like it's trying to kind of reach like an equilibrium.
Let me ask you a question, Ethan. You're sitting on the couch. You're sitting there, you're either playing a video game or you're sitting there watching a tremendous Alfred Hitchcock movie. You're sitting there, you're inert, you are dead. And your mother comes and disturbs you by saying, Ethan, take out the garbage. Are you now agitated, Ethan, because you're doing something you don't want to do?
Yeah.
Would you say that while you're in motion, you're more random? You can do more things when you're standing up than you can when you're sitting, Ethan?
Yes.
So don't you have more energy when you're standing up than when you're laying on the couch?
Yeah.
You have more ways to move. Keep that in mind. We're going to deal right now with spontaneity. So ice melting above zero is spontaneous. Right, everybody? Isn't that true? But as Ethan just said, in order to get that ice to melt, that ice has to absorb energy from the surroundings. It's endothermic. It's an endothermic process in the fact that it is absorbing energy to go to water. It takes energy to do that, yet it's spontaneous. Ethan didn't want to move from the couch to take out the garbage, but he did it because there was something else out there that was making him do it. Think about cats, guys. Who has cats? Who likes cats? Good, Jessica. How many cats do you have? Because there's never
You don't want to know.
There is never such a thing as a one cat family.
I have 6 cats.
Jessica, if you line those cats up, you make them sit down into 2 rows of 3s, and you
Okay.
leave the room, what happens?
They're gonna fight, probably.
Pretty much, Jessica, what the picture is? You can't trust cats to stay in nice little lines of rows. Let me ask you another question. See who else I can grab out of here. Natalia. Natalia? Have you ever spilled milk in your entire life? Did the milk spontaneously go from the glass to the table? Never? You spill the glass of milk. The milk doesn't go out of the glass.
Yeah. Yes.
Does it go back?
No, I need to clean it up.
Now, in which position does the milk have more freedom? Does it have freedom when it's constrained in the glass or when it is free to move on the table?
Free to move in the table.
So systems tend to be random. The more freedom a system has, the more random it can be. You have more freedom when you're up and standing than when you're sitting in a chair. Thank you for smiling, Jenna. We have to get into something called entropy, because if it takes energy to melt that ice, there's got to be something else that we need to take into account that allows that to happen spontaneously. Things don't just naturally happen. You don't naturally transfer energy from one source to the other to get something to happen. There's got to be something else going on. The cheap definition of entropy, everybody knows this, it's chaos. But what we really mean, guys, when we're speaking about chaos is the amount of randomness of a system. Everybody's heard the story of the teenagers that get left home by their parents and they end up inviting a couple people over and things are okay, but somehow those other couple people have invited a couple more people who have invited a couple more, and eventually you have a whole house full of teenagers that are going crazy, drinking beer and destroying lamps. It's gone from a system where we have a control over it because you can control the two friends that you invited over. What you can't control are the 64 that came later. Everybody has their own idea about how much freedom you should have. We are talking about freedom. Think about it. Think about it with COVID. Were you able to do what you wanted to do when you were stuck in that room, in that house alone? Did you have more freedom? Do you have more freedom now than you did then? Not as much as you did before, but you still have more freedom than you have now. You had less entropy when you were isolated in COVID than you do now, because right now you have more freedom. Now, when we're dealing with a system, we're talking about how many different ways you can arrange components so that they're energetically equivalent. That's really what we're talking about when we're dealing with a system's freedom. How many different ways can we arrange things? How many ways can we put those cats in those 2 rows of 3 such that we have them all to be energetically equivalent? They're all sitting in those nice 2 neat rows. Basically, what you can consider are the motions that the molecules have. Again, isn't the puddle of milk freer to move than the milk in the glass? In the 1870s, there was this guy named Boltzman. And what he wanted to do was he wanted to take these movements and look at it at a microscopic level. So he coined this phrase, entropy, that he designated with S. I think he used S because all of the popular letters were taken. And so he set this new term that he called entropy as equal to a constant, which is the gas constant divided by Avogadro's number, times the number of ways of arranging that system equivalent energetically. So he was talking about these little microstates. If we're looking at those molecules up there, they're free to move. The two white ones are able to move equally away. They're able to push together. They're able to yin and yang, and it's able to spin. They have freedoms. How far did you get in this? I got down to FXX and I got lost after that. So what we have to do is we have to look at different systems and be able to rate them so that we can compare one system to the next. If we're dealing with a molecular scale, if you have more kids in the house, you have less control. More particles, you're going to have more states, more entropy. If you have a higher temperature, if you throw beer into the party, then you have even less control. You have more entropy. If instead of confining everybody to the house, the party is able to expand outside into the neighborhood, there's even more entropy, less structure. If we're dealing with a gas versus a solid, a gas has more states it can be in, so a gas has more entropy than a solid. Higher temperatures, more entropy than lower temperatures. More particles, more entropy. So as you increase temperature, volume, number of particles, and as you introduce less structure, you are going to get an increase in the entropy. Increased temperature, increased volume, increased number of particles, decreased structure. That will all involve an increase in the entropy of your system. When you go from gases, from liquids, from solids, you get more entropy. When liquids are formed from solids, more entropy. As you increase the number of gas molecules, you get more entropy. As you increase the moles of your reaction, your entropy increases. Again, number of moles and number of molecules, this is basically the same thing. If you're going from a gas from a liquid, you're increasing, or a liquid from a solid. Do I have any questions so far, ladies and gentlemen? If I dissolve a solid, When I am in a nice rigid solid, I've got a real nice crystalline structure. I've got my little soldiers lined up, my positive ions interspersed with my negative ions, and I have a real nice structure. If I get water in there and it will remove some of those ions from that nice rigid structure, then I get an increase in entropy. There are some exceptions to that. If I have a very highly charged ion that has a lot of water molecules around it, then I am going to decrease the entropy. But as a general rule, if you're dissolving something, you're making more entropy. Again, entropy increases with the freedom of motion. When I have a solid, I have a very distinct crystalline structure, and the molecules have to be within that crystalline structure. They are limited as to what they can do. There's less freedom of motion. So as a general rule, as I am increasing my physical state, gases have more entropy than solutions, which have more entropy than liquids, which have more entropy than solids. Gases, solutions, liquids, solids. That's the rating of this system. Rank the entropies of these systems: water, ice, or steam. Rhea, which of these things has more entropy? Water, ice, or steam? Rate them.
So, ice, water, steam.
Is that an increasing entropy or decreasing entropy?
Decreasing.
You said ice to water to steam is decreasing.
Increasing.
Increasing. Because I'm going to a gaseous state. Now, you are going to have tables. The very back of your book has an appendices with S's, delta H's, and delta G's. And there are heats of formation, entropy, and Gibbs free energy. Understand, in the homework, they do not give you these values. If you want these values, you're going to either have to Google them, or you'd be safer looking them up in the appendices.
Will they be provided on the test?
Yes. As you get bigger, entropies tend to increase with increasing molecular mass. Entropies are bigger with bigger molecular mass because you simply have more particles within that particular system. So I have neon, argon, krypton, xenon, and helium. Sachari, rank those entropies: neon, argon, krypton, xenon, helium. Sachari,
Yes, Professor. Can you? I'm looking it up. Give me a second. 20. Is it increasing?
Tell, they're mixed up, Satori. Look at your periodic table.
N-E. So it's not increasing?
Satori, they're mixed up.
Right.
I've just said in the previous slide that the standard entropies increase with increasing molar mass. So if I'm dealing with the inert gases, which one is going to have the least entropy? I don't know. It's a perfectly good answer, Satori.
I don't know, Professor.
Jennifer,
Yes. You want me to
Please.
tell you?
please.
So I would say the greatest would be XE because it has like a greater molar mass.
Keep on going.
Let me see. Next, I would probably say, would you go with, I don't know if NE would have a greater mass or KR. Let me see on the periodic table. So I would say KR would have a greater mass than AR, and then it would be NE, and then lastly HE because it has the least molar mass.
Going from most entropy to least.
Yes. Did you want least
Biggest mass to lowest mass. Xenon, krypton, argon, neon, helium, just like you said.
Yeah.
This is backwards. I just did it on the slide from least to most. Larger and more complex molecules have greater entropies. So if I have methane, natural gas, that just has a carbon with 4 hydrogens on it. If I compare that to ethane, which has 2 carbons and 6 hydrogens around it, or if I have propane, 3 carbons with 8 hydrogens around it. This is the most complex molecule. It will have the greatest entropy. Next would be ethane, least would be methane. What has more entropy? Argon or nitrogen monoxide? Jana.
Just give me a moment. Argon would have an entropy of.
What did we just say, Jana?
Oh, with higher molar mass, it's going to be lower.
Nope, we're not talking about molar mass. This slide is saying the more complex molecules have greater entropy. What do you think is more complex, argon or nitrogen monoxide?
NO would have more entropy.
More complex, it has more entropy in it. Generally speaking, again, I'm going to mention this again. Generally speaking, if you have a solid dissolving into the liquid, you are going to have more entropy. The one exception is when you get a highly charged molecule that's surrounded by many waters. That tends to be a very organized system. Sometimes you can look at different, they're called allotropes. Different elements exist in multiple forms of the same element. If you are dealing with red phosphorus, everybody here has everybody here lit a match? The fuel for the match is in the head of the match. The red phosphorus is in the striker. But when the red phosphorus is in the striker, it's still exposed to air. It doesn't auto-ignite. Yellow phosphorus, these were very prominent in the Korean War. They had phosphorus bombs that they would go ahead and put yellow phosphorus. And what happens is it would get injected into the bodies and it would auto-ignite as the surgeons are cutting open the bodies, they're dealing with fire because the yellow phosphorus is igniting. Some elements exist in different forms. What you have to understand, you have to define the form that will define the amount of entropy that has. So, ladies and gentlemen, looking at those little brackets that are underneath the elements and just to the right becomes vitally important. Because if you look at that and it says one thing and you look in the table and look up another, your answer will be wrong. We're going to get into now what entropy and the second and third law of thermodynamics is. Been talking about it a little bit. Second law, for any spontaneous process, the entropy of the universe increases. Has anybody heard that the universe is expanding? It has to because of the second law of thermodynamics. The universe has to get bigger in order to increase its entropy. That's a spontaneous process. Spontaneous means it happens right away. It occurs without outside intervention. Spontaneous process is something that occurs without outside intervention. Examples: ice melting above 0 degrees. If you take an object and drop it, that occurs spontaneously. If you just take table salt and put it in the water, it spontaneously dissolves. These things occur immediately, and you don't have to do anything to get the salt to dissolve in water. Non-spontaneous doesn't mean impossible. Vanessa, you out there, Vanessa?
Yeah, I'm here.
Okay, put your image on, or you're on a phone. Vanessa, you still out there?
It's on now.
Okay. Have you ever made a pie, Vanessa?
I think so. Maybe pumpkin pie.
Okay. Did the can open itself?
No,
to
it
get the
did not.
pumpkin. So didn't you have to do a little work to get
Yeah.
the pumpkin out of the can so that you can use it and make the pumpkin pie?
Mm-hmm.
So it doesn't mean that it's impossible to do. Non-spontaneous does not mean you can't do it. If you're making a cherry pie, the cherries don't pit themselves. You have to put in a little work to pit those cherries. Again, Spontaneous processes occur without any outside intervention. If you have two flasks that are connected by a stopcock, you have one that's at a 1 atmosphere pressure, the other is a vacuum. If you open that stopcock, it's natural. I mean, you guys naturally think what happens is that the air is going to move from the full container into the one that's vacuum. And it's going to move in such a manner where you get half an atmosphere on both sides. But you don't go backwards. You don't go from that half an atmosphere on either side into evacuated on one side, 1 atmosphere on the other. It's not going to go back to its original state. This is a hard concept to understand, but you got to kind of wrap your head around it. Is it possible for that to do it? Is it possible? Yes, it is possible. There is one state that exists with the A container being evacuated, the B container having 1 atmosphere in it. But there are so many other states that occur that for all practical purposes, this will not occur. It will not spontaneously go back to its original state. You got to understand something else. Something that happens in one direction may not be spontaneous in the opposite direction. You put a nail out in the Florida weather, it's going to rust, right? Manuel? Put a nail out in the weather, it's going to rust?
Yes.
Have you ever seen a rusted nail eventually going back to being that nice little shiny nail?
Never.
But yet it occurs spontaneously in one direction. It is non-spontaneous in the other direction. So we have to talk about reversible processes. In a reversible process, the system's going to change so that the system and the surroundings can be put back into their original states by exactly reversing the processes. Changes are infinitesimally small in a reversible process. You would have to replicate the process exactly, and it must be done in infinitesimal small increments. Basically, it will never happen. You cannot have a reversible process. But we have to understand that processes that are spontaneous at one temperature may be non-spontaneous in another. Let's think about ice. If the temperature is above 0, do I go from ice to water? If the temperature is above 0, do I go from ice to water?
Yeah.
Anaya? Anaya?
Yes.
If the temperature is above 0 and I have ice, do I make water?
Yes.
If I have ice and the temperature is below 0, do I make water?
No.
So it's spontaneous above 0, non-spontaneous below 0. You can't do an irreversible process by exactly reversing the change to a system because it can't be replicated exactly. So all spontaneous processes are irreversible. Again, you can't replicate the infinitesimal small steps. You can't replicate those exactly. So therefore, the irreversible process can't be undone. Spontaneous processes are always irreversible. Do you have any questions out there so far? Third law of thermodynamics. The entropy of a pure crystalline substance at absolute zero is zero. If you have a pure crystalline substance at absolute zero, where all motion has stopped, the molecules are not moving. They are just in that crystalline pattern. In other words, there's only one way, one freedom that that system can have at that point. From Boltzmann equation, the entropy is equal to his constant times the ln of the number of freedoms. If there's only one freedom, you get the ln of 1, which is 0. So the entropy is 0. The entropy of a pure crystalline substance at absolute zero is 0. That is the third law of thermodynamics. So basically what it comes down to, the first law says you can't get anything without working for it. Second law says the most you can ever accomplish by working is to break even. The third law says you can't even break even. Can anybody define what Hess's law is? Leonardo, do you remember Hess's law from Chem 1?
I don't remember it.
Don't remember it? Ethan?
I don't quite remember it either.
Tell me what you remember of it. Jenna?
Yeah,
Sorry, go ahead, Ethan. Do you know something?
no, just go ahead.
Jenna?
Is this the one with like the sum of the products minus some reactants? Is that it? Okay.
That's exactly it. Hess's law says for the enthalpy, if I want to know the enthalpy of the entire reaction, I'm going to take the enthalpy of the individual molecule, multiply it by the coefficient within the compound. I'm going to take all my products, add them all up, and I'm going to subtract out all my reactants. Does this sound vaguely familiar to you guys? Benita?
A little bit.
A little bit? Okay, a little bit's all I'm asking for at this point. Emily, does it sound familiar?
Yeah, a little bit.
Manuel?
Yeah, I remember this.
So these are all state functions. A state function is a function that it doesn't matter how you got somewhere, just that you got there. Benita,
Yes.
have you ever wanted to go to Washington?
Yeah.
Okay. You're on a road trip, Benita. You're going from here to Washington. Right?
Okay.
If I have to, yeah. I even have a map to help you.
Oh, fantastic.
Which way are you going to go, Benita?
Where is Washington?
Where's Washington?
Up.
You guys, you young people.
Yeah.
You don't have any geography.
No. Stop.
How are you gonna get there, Benita?
Going north. Stop.
Tell me where. Which states?
Oh, I gotta go through Georgia, South Carolina.
Oh dear God.
No?
Look, wait.
Maybe we should
Benita.
ask somebody
I
else.
think you're thinking
Sorry,
Washington,
Benita, look,
D.C.
this is
Oh,
not
you don't mean
DC.
Washington, D.C.?
No, Washington State.
Oh.
There is another Washington other than DC.
Oh, wow.
So
No, I
where
don't
you got?
wanna
Which way
go
you
there.
gonna go?
Maybe somebody else.
Manuel, tell me how you're going.
I'm gonna go through Georgia. Oh, I'm
Okay.
thinking like of the interstate, right?
No, just you're on
Just
a road
straight?
trip. You're on
I'm
a road trip. Go
gonna do-
whichever way you want.
All right, Georgia, and then a little bit of Alabama, Tennessee, Missouri, Kansas, Colorado, Wyoming, Idaho, and Washington. Just like that.
Colorado, Idaho. Okay. Basically, you kind of went this way, right?
Yep.
Right?
Yep.
All right. Natalia, how are you going?
I was thinking the same way.
Nah, you're not in Jordan. Tell me some way. How would you go?
Mm,
A different way?
Yes.
Okay. Maybe Alabama,
Let me get my arrow. Alabama.
Mississippi,
Uh-huh.
Arkansas.
Oh, you would avoid New Orleans? Oh.
Well, you said
These
anyway.
people, man.
Okay, we're going from Mississippi. I can't believe you're in Mississippi and you're not going to New Orleans. But that's
got a
fine.
better
If
route.
that's the way you want to do it. We're going from Mississippi to Arkansas. Where are you going from there?
Oklahoma.
Oh, dear God, no.
Hey,
Have you
you
been to
said
Oklahoma?
anyway.
Have you been to Oklahoma?
I have never been anywhere outside of Florida, so you really picked like the wrong person.
Okay, where are you going from Oklahoma?
You can just go straight up. So Colorado, Utah, Idaho, Washington.
Okay. Did they choose the same routes?
No.
Okay. Now, did their latitude change the same? They started in Tampa, they ended in Seattle. Did the latitude difference between the two of them, is it the same?
No.
You start in Tampa, you end in Seattle. So if I take the latitude of Seattle and subtract the latitude of Tampa, did it matter which way they took to get from Florida to Seattle?
No.
It's a state function. See, we have the states here. I got a smile from Manuel anyway. We have the states here. It's a state function. A state function says, I don't care which road it took for me to get there, just that where I started and where I ended. Those are the only things I need to worry about. So we're going to do the same thing with entropies involving Hess's law that we did. We're going to do the same thing with entropies that we did with enthalpies. Hess's law does not change. And keep this in mind. Hess's law also works for delta G's as well. So what you're going to do to find the delta S of your reaction, you're going to sum all the delta S's of your products, and you're going to subtract the sum of all the delta S's for your reactants. Now, there is something that you need to note. Delta H of formation for pure elements in their natural state is 0. Again, I will repeat that. The change in enthalpy of formation for pure elements in their natural state is 0. That is not true of S's. Because remember, we're relating S's from the third law of thermodynamics. We're relating it to the S at absolute zero. Again, we're going to find them, the components, in a table. I will give you these on the exam. So, what is the change in entropy when hydrogen reacts with chlorine to make hydrochloric acid? My delta S's. Hydrogen at a gas. If I was doing delta H's, that would be 0, and the Cl2 would be a 0. But it's not enthalpy, it is entropy. So what I'm going to do, I look in the table and I find that my hydrogen has an entropy of a positive 130. Chlorine has an entropy of a positive 223, and HCl has a positive entropy of 186.9. So to do this problem, I'm going to see the coefficient in front of my HCl. I'm going to multiply my entropy by that coefficient. There's no other products, so that's the only thing on the product side. From this, I'm going to subtract. The coefficient in front of H is 1, so I'm going to subtract a total of 130, coefficient in front of Cl. 1 times 223. I'm going to set that up. The 186.9 is my HCl entropy. I have to multiply it by 2 because my coefficient in front of HCl is 2. From that, I'm going to subtract out my entropy of my H2 multiplied by 1 because that was the coefficient, plus my entropy of Cl minus, or Cl2, multiplied by 1. I add all this up and I get a positive 20.7. Is this starting to become familiar to you? Are you starting to remember doing problems of this ilk? Jordan, you good with this? You remembering it? Rhea, do you remember it?
Yes.
Parker, you good?
Yeah, I'm good.
We're going to start to get a little complicated. Remember, I said you had to be very, very careful. You have to be very, very careful because you're going to get a table and your table is going to have different states. So Parker, I'm going to do my products first. We're going to look at CO2, Parker.
All right.
What am I going to multiply my entropy by?
You said for CO2?
CO2.
It is the 213.8.
I got to look, it's the gas. I got to find the one with gas. So I have to multiply 8 times 213.8. That is the CO2. Raylena, what about water?
Um, 188.8
Times
10.
times 10. That's going to be the entropy of my products. Emily, C4H10.
310 times 2.
310.
Yeah.
Very good. You looked at the right one. 310 times 2. So I'm subtracting that part away. Anaya, what about my oxygen?
Are you subtracting it as well?
It's a reactant. Reactants get subtracted out. What's the correct entropy for O2? Gas.
Oh, I'm not sure.
You see the table, Anaya? Anaya, do you see
yes,
the table?
yeah,
So
I do.
what's the entropy?
Oh,
Approximate.
205.
What am I multiplying that by?
13.
13. So I do that math out. I take my 8 times 2, 13.8. To that, I add 10 times a positive 188.8. From that, I subtract the sum of 2 times 310 plus 13 times 205. I add all that up. I get a positive 313 joules per mole. Any questions? Any questions, ladies and gentlemen? Questions on doing a straight Hess's law equation? Okay.
Wait, so it's just pretty much products minus reactants and then algebra, right?
Yeah.
That's just pretty much
Well,
what
it's
it
not
is.
even algebra. It's not even really algebra. It's just a math problem
Oh, okay.
because you're not solving for X, really, are you?
No.
All you're doing is multiplying and adding, right, Manuel?
Yeah. Well, distributing. Yeah.
Still, distributing is a math problem.
Yeah.
Any questions? Fairly confident? Are you fairly confident in doing these? All right, now we got to do the other type of Hess problem. And this is calculating entropy from other reactions. Okay. Oh, dear God, what did I do? Okay. I have these three. I want to see how I did this. Okay. For the moment, do not pay attention to the bottom numbers there for the moment. All right. I have my overall reaction. My overall reaction, the one I want to know what the entropy is NO plus a single O yielding NO2. I have three reactions that I need to manipulate and then add all three of those together so that I get NO plus O yields NO2. I have these three reactions. Now, how do you do this? We're going to rearrange so we cancel out all the unwanted compounds and elements, and there are some rules. If you reverse the equation, you must reverse the sign of the entropy. If you flip a reaction, if the entropy was positive, you have to make it now negative. If you multiply or divide the equation, you must also multiply or divide the entropy. So, my original equation, I got to look at my three reactions and make this one. Can anybody see which reaction has an NO in it?
The top one.
Manuel, is there the right number of NOs in there?
Yes.
Leave it alone. NO only occurs in the top equation. It is the right number. So it's going to stay like that. Okay? Now, can anybody find an O in those three equations?
Like a single one?
A single O.
A third one?
Third one. Who's answering this?
Me? Jess?
Jessica?
Yeah.
Okay, Jessica. Is the O on the right side?
Mm-hmm.
Okay. Is it on the correct side?
Yeah.
Which side is the O on our target equation?
Oh, it's on the product side.
In
Or
our
reactant
target,
side,
it's on the reactant side.
Yeah.
And in our,
So it's on the wrong side.
it's on the wrong side. I have to flip that reaction.
Okay.
Is there anything else I have to do to that reaction?
I don't know.
How many O's does it have?
Just two.
How many does this one have?
Just one right there. But
I
there's
have
another
to
one.
make
with
them
an extra.
equal. I have to make them equal. So what do I have to do to this reaction? How do I make 2 into 1?
Cut it in half.
Divide it by 2. So not only for this third reaction, not only am I flipping it, I'm going to divide it by 2.
Okay.
So this, I flipped the reaction. I've divided it by 2. So I'm good with my reactants. My NO is on the right side. I've got the proper number of O's on the, I'm sorry, my NO is on the left side. I've got the proper number of O's on the left side. Coincidentally, I also have the proper amount of NO2s on the right side. At this point, all I have to do is cancel out what's in common on left and right. I've got an O3 here and O3 there. I've got one O2, which is the same as 2 halves. I had 2 halves O2 with a half O2. I get 3 halves O2 on the right. I have 3 halves O2 on the left. I have got my problem solved. So all I have to do is find my entropy of my first reaction, second reaction, and third reaction. Add them up. I will have my entropy of this overall reaction.
So on a, I have a question. So on the quiz or test, you're gonna give us 2 or 3. Are these called elementary? Huh?
On the quiz or test, what I would give you, Manuel, I would give you
Are these the same as elementary steps? Is this
kind of, sort of.
okay?
It's not really. What it is you can find a table to look up these. What I would give you is, do you see what I have highlighted, Manuel?
Mm-hmm.
I would give you this, and over to the side, I would give you what the delta S is for each one of these reactions is.
Okay.
Remember, we flipped this one and divided by 2. So I'd have to take what the delta S is of that third reaction. I would have to flip the sign of it and divide that by 2, because that's what I did to the reaction. I think I did something strange for this one. I did. What I did was I used the individual delta S's for NO2 and O2, subtracted out the delta S for NO and O3. That's how I got the delta S of the first reaction, which was a negative 3.5. Second reaction, I have 3/2 O2 yielding an O3. So for the second reaction, I have, this is the S of O3. It gets multiplied by 1. I subtract out the O2 had 3/2 multiplied by the S of O2. That ends up being a negative 69.8. Third reaction, I have third reaction, I have O going to 1/2 O2. So for the third reaction, I'm sorry, I'm trying to find this silly thing here. For the third reaction, I've got 1/2 of the entropy of O2 minus 1 times the entropy of O. I subtract those out and I end up with this. Last step, I have to take each one of these entropies, add them all up. That is my total entropy for the reaction. Questions on this, ladies and gentlemen?
I'm confused on the canceling out part because you said we would cancel out the O3s, but we're still adding them in the equation.
We canceled them out to make sure that these 3 would equal this one. Okay?
Oh, I see.
Who's
Yeah, I
asking
see.
the question?
Emily.
Emily, okay. O3's on both sides. The 3/2 O is on both sides. So if I cancel those out, what I'm left with is NO plus O yielding NO2.
Right.
Correct, Emily?
Yeah.
But you have to understand, I know the entropy for these 3 guys. Okay?
Mm-hmm.
So if I know the entropy for these 3 guys, all I have to do is add them up. That will give me the entropy for this one since everything canceled out. Does that make sense, Emily?
Yes, it does. Thank you.
Anything else, ladies and gentlemen?
Professor,
Yep, I'm here.
is there a way we can do another example, or is there going to be more examples in the PowerPoint?
I don't think I got one. Can you bear with me a second?
Yes.
All right, Araceli. All right, guys, one more slide. And what I'm going to do is I'm going to pull up an example from enthalpy. Remember, enthalpy is going to work the same way as entropy. You have to note this though. Delta S's are in joules per mole K. Delta H's are in kilojoules per mole. Delta G's, when we get to them, are also in kilojoules per mole. Okay? So you have to remember that we have to change. If we're adding an H to an S, we have to make sure that we change the S's to kilojoules. And the other important facet, delta S of an element in its natural state is not necessarily 0. Okay, so I'm going to get out of here and I'm going to try and find something for you. Okay, summer 24. Nope. Okay. Just bear with me, guys. I just have to go through and find it. Okay. Again, I am doing this with enthalpies. Understand, I can apply them to entropies. Okay, I have the combustion. This is a simple one, too simple. Maybe it isn't. Okay. All right. I have this overall reaction. Araceli. You ask Araceli, so you got to participate. Araceli?
Yes.
Okay, you asked, so you got to participate.
Okay.
This is my overall reaction at the top. Okay?
Mm-hmm.
These reactions down below are the ones that I know the enthalpy. Okay, Araceli?
Yes.
So, first thing I'm going to do is I'm going to look at my first reactant. And I'm going to look at my 3 reactions down below here. Araceli, where do you find carbon?
On the first equation?
Is it in the right? Is it on the right side of the arrow? Okay,
Yes,
so I don't have to flip it. Do I have the right number of them, Araceli?
No.
So I got to multiply this whole top equation by 2.
Okay.
Okay?
Yes.
I do that, and I have now gotten my new enthalpy. Okay? What about the H2, Araceli?
The H2. So, can you go back, Professor, on the other, or is it the same?
It's the same one. What I've done, Araceli, I've done the change. You told me to multiply the first reaction by 2. I did that here.
Okay.
All right. Now, this is still the overall reaction. Do you see the other reactant?
Yes, H2.
How many is that on the same side?
Yes, it's on the same side.
Okay, so what am I going to do with that second reaction?
You're going to have to multiply it by 3, right?
And I did. I multiplied it by 3. Understanding, I got 3 halves O2 as well and 3 H2Os, right?
Yes.
Okay, now Araceli. I've taken care of my C's. I've taken care of my H2s.
Mm-hmm.
The only thing left is my C2H6. Is that on the correct side?
No.
So I have to flip it.
Okay.
I flip it. Notice my sign went from a negative to a positive. Okay, Araceli?
Yes.
Now, is my number of C2H6 correct?
No.
So what do I have to do to the bottom?
Divide it by 2.
I divide it by 2. This gives me my new enthalpy. Add up everything. I got 2C plus, this gives me 2 O2s is the same thing as 4 halves O2. Okay. I've got 3 H2s. I got 3 half O2. 2 CO2s, 3 waters. On the other side, I've got 2 CO2s, 3 waters, C2H6, and 7 halves O2. Araceli, is there anything that's the same on left and right of this equation?
No.
No?
I mean, yes.
Look, this is all. Is there anything that's on the left? Understand, everything on this line is on the left side of the arrow. Everything on this line
It's on the right.
is on the right. Is there anything that's on the left and right that's the same?
Yes.
What?
For example, 2 CO2.
2 CO2s. I'm going to get rid of that. Anything else the same?
3 H2O.
3 H2Os. I'm going to get rid of that. How about the O2s?
They're the same as well.
4 halves and 3 halves equals 7 halves. So literally speaking, that equals 7 halves. That's going to cancel with that O2. That CO2 is going to cancel, and my waters are going to cancel. The only thing that's left is 2 C's, 3 H2s, and a C2H6. At this point, all I have to do is add up the entropies, and that gives me my entropy, my enthalpy of this reaction.
Okay.
Any other questions? Does anybody want me to go over another one? Or are you pretty good with this? Again, I don't have any specific entropy ones prepared, but I do have enthalpy ones. Nope. That's not the one I want. Okay, guys, are we good? I'm just looking here to see how many slides I have to go through. Okay. Okay, now we're going to deal with entropy and spontaneity. The entropy of the system and the entropy of the surroundings are going to determine the entropy of the universe. Surroundings and system added together equal the system of the entropy of the universe. Now, we have to define system. A system is whatever we're observing, and only that. The surroundings means everything else in the universe. So my change in S universe is going to be equal to my entropy of my system plus my entropy of my surroundings. Remember, second law of thermodynamics stated the entropy of the universe increases for spontaneous processes, irreversible, real spontaneous processes. Delta S is going to be positive. I need delta S universe to be positive in order for my in order for my reaction to be spontaneous. And we're going to be dealing with the law of spontaneity over the next 2 chapters. If I have a reversible ideal reaction, my change in universe, my entropy of the universe will be equal to 0. I'm at equilibrium. But you can't break even. There is no perpetual motion. Again, if I have an ideal reversible process, my change in entropy of the universe will be 0. Irreversible, spontaneous is going to be, my S of my universe is going to be greater than 0. Important concepts. You have to get these down. If S is positive, you have a spontaneous process. If S is 0, you have an equilibrium. What you have to understand is that for individual systems, entropy can decrease if S of surroundings is big enough to compensate for it. So I can have a spontaneous reaction if my delta S of the system is negative, but my delta S surroundings is larger and positive to overcome it. So what happens if the entropy of the system is negative? Right? Entropy is negative. We said earlier on today that when we go from a liquid to a solid, my entropy is decreasing. Right? So what must happen is the effect of my entropy on my surroundings must be increased and must be larger than the entropy of the system in order for that process to be spontaneous. Again, if you have a negative entropy of your system, like ice forming from water, what has to happen in the surroundings? The surroundings entropy must increase and it must be larger than the entropy of the system in order for your delta S universe to be positive and be spontaneous. So how does the entropy of the surroundings increase? When you cool water to ice, that releases energy. The ice has less energy than the water does. That energy has to go somewhere. So that energy is dispersed into the surroundings. Temperature of the surroundings increases. Therefore, the entropy of the surroundings increase. An exothermic process acting on the system increases the entropy of the surroundings. An endothermic process acting on the system decreases the entropy of the surroundings. Think about it this way. My system is exothermic. It's releasing heat. Surroundings temperature, even infinitesimally. If that increases, then my surroundings entropy has increased. On the other thing, if I have a positive delta S in my system, then I have to put energy into that. The energy comes from the surroundings. which decreases the entropy of the surroundings. Basically, entropy is a term coined by this clown in the 19th century. And what he was really interested in is he was interested in the ratio of heat delivered versus temperature. Okay, it's kind of like it's harder to put heat into something that's already boiling than it is to put heat into something that's at room temperature. That's basically the problem he was interested in. And eventually we're going to develop Gibbs free energy from this. Now, when a system absorbs or emits energy, it either takes energy from the surroundings or it gives it. So, the system acting on the surroundings, the sign is going to be opposite. Whatever's happening to the system, the opposite effect is happening on the surroundings. So if my entropy of my system is Q divided by T, my entropy of the surroundings is going to be negative Q over T. At constant temperature and pressure, Q of the system is simply delta H. At constant pressure, the heat, the Q, is being dealt with by a system is simply the delta H of that system. So I'm going to plug in negative delta H over T. I'm plugging in negative delta H over T for my delta H surroundings. This gives me this equation. I multiply all the terms by T delta S. I'm sorry, by T. I multiply each one of these terms by T. I get T delta S universe is equal to T delta H system, delta S system, plus my negative delta H. T delta H universe, by definition, is negative Gibbs free energy. So if I multiply each one of these terms by a negative, I get negative T delta S universe, which is Gibbs free energy, is equal to delta H minus T delta S. This is the equation we're going to need. So, remember we said for spontaneous processes, delta S is positive. Parker, if for a spontaneous process, delta S universe has to be positive, what is the sign of delta G?
Would it also be positive?
Delta G is equal to negative T delta
Oh,
S.
so it's negative then.
All right. Understand that, guys. Delta S universe positive, spontaneous. Because there's this negative sign in front of it to equal delta G, that means that my delta G has to be less than 0. You can't determine the entropy of the universe. Can't be done, but you can determine delta G. So we're going to use delta G to determine if a process is spontaneous or not. When delta G is negative, spontaneous. When delta G is positive, non-spontaneous. So we're going to be able to predict spontaneity based on enthalpy, entropy, and temperature. This is the last thing I'm going to get into, and then we're going to stop for the day. Remember our formula. Delta G is equal to delta H minus T delta S. If H is positive, if we have an endothermic reaction, and S is negative, Jordan, you there?
Yes, sorry.
If H is endothermic, in other words, delta H is positive, and S is negative, what does the sign of delta G have to be?
Is it negative?
What's the sign of delta H, Jordan?
Positive?
And I'm subtracting what kind of number from it?
Negative?
So I'm subtracting a negative number from a positive number. What is delta G?
Positive?
Positive. It doesn't matter what the temperature is in these circumstances. Delta G is always going to be positive because delta H is positive and I'm subtracting a negative number from it. Delta G is always positive. This will always be spontaneous, non-spontaneous, Raylena.
What was the question?
Delta G is always going to be positive. If delta G is positive, do I have a spontaneous or do I have a non-spontaneous process?
Non-spontaneous. Non-spontaneous.
Non-spontaneous, exactly. Okay. Look at the reaction. It's an endothermic reaction. Under what conditions will this reaction be spontaneous? Ethan. You out there yet, Ethan? Leonardo. Am I taking roll?
Here.
Thank you. Who was that, Leonardo or Ethan?
That previous one was Leonardo.
Okay, Ethan, you're there. Okay. Let's look at this. It's an endothermic reaction. What is the sign of delta H?
Plus delta H.
Plus delta H. Okay, look at the reaction. Do I have more particles on one side or the other?
You have more particles on the reactant side.
Okay, if I have more particles on the reactant side, then what is the sign of delta S?
It's
You have more cats in a room.
you
have more of the kids in the house party. Which do you have less control over? 2 kids or 64?
Oh, okay. So positive delta positive S.
Which one? I have more kids on the left going to less kids. Remember, it's always products minus reactants.
Oh, okay, okay. So negative like delta S.
I have a negative delta S. I have a positive endothermic reaction and my S is negative. So Ethan, what is the sign for my delta G going to be then?
It's going to be positive.
It's going to be positive. If it's positive, Ethan, is it spontaneous or non-spontaneous?
It is spontaneous. Or wait. Oh wait. No. Like if G is. Oh wait, no. G is above 0. It's okay. It's non-spontaneous then. Yeah.
Non-spontaneous. All right, if H is negative, delta H is negative in exothermic reactions and S is positive. That means I have a negative delta H subtracting a positive S. Negative subtracting a positive number, delta G will always be negative. It's going to be non-spontaneous under all conditions. Hold on a second, guys. I want to make sure I don't screw you up. Okay. I have an exothermic reaction. Under what conditions will this be spontaneous? Remember, we're looking to find delta G. Exothermic reaction. What's the sign of delta H? Emily. Emily?
It's negative.
Delta H exothermic is negative. Okay, Emily.
Yes.
How many particles do I have on the left?
12.
How many on the right?
10.
This one doesn't really count because it's a liquid.
Oh, right. It's liquid. Yeah.
So I
So
have
9.
12 on the left, 9 on the right. What is happening with my delta S? Is my delta S increasing or decreasing? Again, do I have more kids in the party or less? What do I have more control over?
It's increasing the delta S.
My delta S is increasing. So my delta S is positive and I got a negative. I've got
So
it. Go ahead.
the delta G is going to be negative.
Delta G
And
is going to be negative
it's going to be spontaneous.
under all conditions. Did you all get that? Delta G positive, we have non-spontaneous. Delta G negative, we have a spontaneous reaction. And I think I have a misprint in here. That was what was screwing me up. If delta G is negative, we have a spontaneous reaction. I knew there was something screwing me up.
I thought I
Sorry.
It's okay.
Delta if delta G is always negative, it's going to be spontaneous. when I have an exothermic reaction, delta H is going to be negative. If delta S is positive, I'm subtracting a positive number. Delta G will always be negative. It's always spontaneous. Now, consider this reaction. If I have delta H positive, if I have an endothermic reaction and my delta S is positive, I have two conflicting things here, don't I? Rhea, do I have two conflicting things here? I've got my delta H is positive and my delta S term, because I'm subtracting it out a positive number, that's going to be negative. So I have two conflicting things here, don't I, Rhea?
Yes.
Now, that's where the temperature comes into effect. Consider this. If I get my temperature high enough, isn't my T times my positive S, isn't it possible that that will overcome my positive delta H to make the overall delta G negative? Does that make sense, Rhea?
Yes.
Natalie, does that make sense?
Yes.
Let's see who else is out there. Benita, are we making sense here?
Yes.
Benita, has it been 2 hours? Been 2 hours? You want to stop this?
Yes. Yes.
Okay. I got one more to go through after this, all right? So, Benita, are you seeing if my temperature is high enough that this second term, it may not matter what delta H is, the second term, because I'm multiplying by a high temperature, that's going to make this overall thing negative. Does that make sense to you, Benita?
Okay.
So if I have my reaction that is endothermic and I have an increase in my entropy at high temperatures, because the high temperatures is going to make the second term larger than the first, at high temperatures, I'm going to have a negative delta G. It will be spontaneous. On the other hand, if my temperature is low, that's going to make the second term even smaller. If it's small enough, the H is going to be larger. My delta G will be positive. So under these circumstances, high temperature, high temperature, positive delta G, spontaneous. Low temperature, negative delta G, non-spontaneous. I think you all have had it right now. You're pretty fried. I'm going to start up with this on Tuesday. We're going to start up with this on Tuesday and continue on from there. Do I have any questions? If that's it, guys, then that is it. I will see you on Tuesday.
Thank you.
Thank you.
Be
Thank you.
prepared. Let me wait before you go. Real quick. Aethor I saw. And now Jordan I saw. Vanessa, Natalia. Benita, obviously I saw. Jenna, Jennifer,
Yeah.
Manuel, Parker, Araceli, Jessica,
Here.
Valeria. Valeria. Jana was there. Leonardo was there. Anaya, Natalie, Sachari, Raylina, Maria, Emily, and Ethan. Okay, bye.
All right.
Bye.
Bye.
Professor
Who's speaking?
Sachari, I know you mentioned that you were considering doing an extra credit for the last test. So would you just send an announcement if you do,
I
when
will.
you're gonna do and everything?
It will be sent probably tomorrow, Sachari.
Okay, no problem. See you in class. Bye.
See you in class.
I also have a question. It's Jennifer.
Hi, Jennifer.
So I saw that you posted a total of 6 discussions due on the 27th.
I did that, Jennifer. Just all you need is 3.
Only 3? Okay, how
Only
about
3. The reason I did that, Jennifer, was because I wanted to give those extra homework things to give you a chance to see what a question would be. That's all.
Okay.
You don't
So-
have to answer it's just 3 per week.
So would you recommend doing them this week, or would you post a new one for this week?
Talk about what we've discussed here, okay?
Okay, so just like create a new one and then go off of that.
Yeah, to be honest with you, Jennifer, from what I've done so far, I don't really have anything that I could do a Hess's problem for you, but that would be it.
All right, sounds good.
Okay?
Professor?
Yes, Araceli.
Sorry. I was just looking at discussions, but it was the new ones you posted. It said June 27th? Because I don't have any for July.
Araceli, I just explained that to Jennifer.
Sorry.
And what was happening is I wanted to give you some last minute questions if you wanted to address them. So
Okay.
that's what that was about, okay?
Okay.
Don't worry about it. If you're giving me 3 a week, that's all you need.
Okay. Sounds good. Thank you.
And then how long, if you were to do the recording on Tuesday, how long would it take you to approximately like post it? Would it take you?
Recording on Tuesday.
Yeah, for next Tuesday.
Jennifer, it's been really, really hit and miss. You've seen what happens is, literally speaking, Jennifer, I work from 8 until 5. Okay, Jennifer?
Okay.
And as a consequence, what happens is when I'm at 5, my mind is fried. So I do not get to that until the next day. If something occurs the next day to interrupt me, then it doesn't get posted. For example, the last lab.
Yeah.
I had, literally speaking, did you see how quick it went up?
When you posted it, yeah.
All right. The reason it got posted so quickly is I had done everything except load it from my computer files into the course program. I'd gotten that far into it that all I had to do was the next step.
Yeah.
So I apologize. I get them to you as quick as I can, but that is what's happening. Basically, right now I'm having to deal with getting this. Okay, because the turnaround time, especially from this morning, was so short, though that the Zoom program from that did not get uploaded. Okay, Jennifer? This one is probably not going to get uploaded because I'm going to have to leave for Dale Mabry
lab, yeah.
by 1 o'clock or so. So this may not get loaded up. So that entails my having to figure it out tonight or tomorrow morning, what I've done or haven't done.
That's fine.
I will do it the best I can, okay? If you don't see it within a couple days, email me and that will remind me, hey, I didn't do it yet, okay?
All right, so I'll just keep checking when the day approaches, and like Wednesday, if I haven't seen that you posted, is it okay if I email
Yeah,
you?
absolutely.
Okay.
If I haven't emailed it by Wednesday, if I haven't emailed Tuesday's lecture by Wednesday, 5 p.m., by all means, free reign.
All right, because I don't want to like be missing anything. So
No problem. Have fun in the Dominican.
I'll try. I have a lot of homework that I'm trying to do this week, but the professors literally post it the week of, and she's not gonna post it a week in advance so that I could work on it. And it's
Jennifer,
kind of tough.
yeah, I know it's kind of tough, Jennifer, but you chose this.
Yeah, I did. So it's okay. I'll work something out.
It'll get done. You're
Yeah.
smart enough and you're organized enough, Jennifer, that you will get it done.
Thank you. I appreciate it.
All right, take care. I will see you. Am I seeing you on Tuesday?
No, Tuesday no, but Thursday for sure.
All right. You
All
take
right.
care of yourself now.
Bye.
Bye. I have to take a shower, so that's one of the things I need to do. Huh?
I can't do that for you.
Um,
What kind of sandwich would you like me to make?
I